So, what's really the difference between the brain in your laptop and the one in your coffee maker? I mean, they're both processors, right? Well, one is a powerhouse that you have to build a whole system around, and the other is a self contained specialist. Today, we are breaking down that crucial difference between microprocessors and microcontrollers. All right, here's how we're going to tackle this. First, we'll look at the big picture choice. Then, we'll dive into the hardware that makes these two chips so different. We're going to get our hands dirty with a classic, the 8051, and even map out its memory. And finally, we'll see why making the right choice here is critical for pretty much every piece of tech you own. Okay, Section 1. Two brains, one choice. Before any engineer even thinks about a circuit, they have to answer a fundamental question. This isn't just about picking a part. It's about choosing an entire philosophy for the product they're building. And honestly, this analogy just nails it. Think of a microprocessor like you're building a custom gaming PC. You start with a super powerful CPU, but then you have to add everything else. The memory, the storage, all the ports. It's incredibly powerful, and you can customize it endlessly. But a microcontroller? That's your Swiss Army knife. Everything you need for a very specific job, the blade, the screwdriver, the can opener, it's all folded into one compact, super efficient tool. So how does that PC versus Swiss Army knife idea actually look in silicon? Well, it all comes down to what's baked into the chip itself and what you have to add on the outside. This picture tells the whole story. Look at the left side. The microprocessor is just the central processing unit, the CPU. It can't do anything on its own. It needs all these external chips for RAM, for ROM, for I/O, all connected by a web of wires. Now look at the right. That microcontroller has everything right there on the chip. It is, quite literally, a computer on a chip. And that right there leads us to the big trade-off. A microprocessor's superpower is its versatility. You need more memory? Just add another chip. You need a different kind of port? Plug it in. But the microcontroller's superpower is efficiency. It's designed from the ground up to be cheap, to be small, and to sip power, which is exactly what you want for a device that only does one thing. Now, if you're studying for an exam, this table is gold. It just lays it all out. Look at how one thing leads to the next. Components, CPU only versus the whole shebang on one chip. That directly affects the system cost. High for the microprocessor system, low for the microcontroller. And that leads to flexibility. High for the customizable system, but low for the fixed all-in-one chip. It all boils down to the target use. General purpose computing versus single-task embedded systems. And this is the world where the microcontroller is king. An embedded system has one job, and one job only. Think about your microwave, your TV remote, the controller for your car's anti-lock brakes. They don't need to check your email. They just need a tiny, hyper-efficient brain to run a single program, perfectly, for years. So to make this all really concrete, let's zoom in on an absolute legend, the Intel 8051. Now, this isn't just some random chip. This is one of the most influential microcontrollers ever made, and its design ideas are still found in modern devices today. And here it is. This is the blueprint for the 8051. See? All those blocks we've been talking about are right here on this one diagram. You've got the CPU in the middle, 4 kilobytes of ROM for the program code, a tiny 128 bytes of RAM for data, timers, I/O ports, everything a complete system needs is right there. These are the specs. If you were an engineer back in the day picking an 8051, this is what you got. Period. No upgrades. You couldn't just add more RAM if you felt like it. And these constraints, they weren't a bug, they were a feature. It forced developers to be incredibly efficient, and it made the chip insanely cost-effective for millions of products that could live within these limits. Okay, let's go even deeper into that fixed architecture. How on earth did engineers manage to do anything with such a tiny amount of memory for data? The secret is in its incredibly clever organization. Just let that sink in for a second. 128 bytes. Not kilobytes, not megabytes. Your smartphone has billions of times more RAM than this. This single tiny constraint is what led to a beautifully structured memory layout, because every single byte had to be used as efficiently as possible. And here's that layout. This map shows that those 128 bytes, from address 0 all the way to 70F and hex, are not just one big messy pile. Oh no, they are meticulously divided into 3 very distinct sections, and each section has a very specific job to do. Let's break it down.
All right, let's walk through this. The first 32 bytes are set aside for working registers, which the CPU uses for super fast calculations. Then, and this part is brilliant, the next 16 bytes are bit addressable. This means you can flip a single bit from a 0 to a 1 to, say, turn on an LED without messing with the other 7 bits in that byte. It's incredibly efficient for control tasks. And finally, you get the remaining 80 bytes as a general-purpose scratchpad. This whole structure isn't just a memory map. It's a masterclass in clever engineering under extreme constraints.
So, we've seen the powerful, flexible microprocessor and the constrained but efficient microcontroller. And that brings us all the way back to the most important question for any designer. Why would you ever choose the limited option on purpose? Well, the decision is never just about who has the most raw power. It's a balancing act. Is this chip fast enough for the job? Is its power consumption low enough for a battery? Does it have the right amount of built-in memory and I/O? And maybe most importantly, what is the cost per unit? Because when you're making millions of something, saving even a nickel on a chip is a massive deal.
And this quote just sums it all up perfectly. The space, the power, and the price are much more critical than the computing power. That's the whole ballgame. For most of the electronics in our lives, efficiency beats raw power every single time. You don't need a supercomputer to run a washing machine. You need a cheap, reliable, low-power brain. And that is the kingdom of the microcontroller. So here's the real takeaway. While the big, beefy microprocessors in our computers get all the headlines, it's the humble microcontroller that is quietly running the modern world. They are the unsung heroes, the hidden workhorses inside dozens of devices you use before you even finish your morning coffee. So take a look around you right now. How many of these tiny, dedicated brains do you think you've already relied on today?